Swayam Prabha. Digital India. Educated India.
We have discussed polynomials before. We will continue our discussion on polynomials in this class. Previously, we have defined polynomials over fields. First, you should note that polynomials can also be defined over arbitrary rings. If R is a ring, then a polynomial over R is an expression a n x power n plus a n minus 1 x power n minus 1 plus dot 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 up to a naught, where a naught, a 1, all these coefficients are from the ring R. So, set of all such polynomials over R, meaning with coefficients from R, is denoted by R x. And we have already defined for fields, polynomials over fields, we have already defined addition and multiplication operations. Same addition and multiplication operations are defined even for polynomials over rings, and under those addition and multiplication operations, one can easily check that this forms a ring as well. The set of polynomials forms a ring. Now, if there is some basic relationship between the original ring R and the polynomial ring R x, and we will first mention these as a theorem. So, R is a ring, then the ring R x is commutative if and only if R is commutative. R x is a ring with identity if and only if R is a ring with identity. And third is that R x is an integral domain if and only if R is an integral domain. All these results are very easy to prove using just the definitions. For example, R x is commutative if and only if R is commutative. First, it is clear that as a ring, R is a subring of R x. This is a subring. Under the same, the operations in R can be also seen as restrictions of the operations of addition and multiplication operations of polynomials. Just the elements in R happen to be specific types of polynomials, which are just these a naught constant polynomials. So, if all polynomial multiplication is commutative, then clearly the multiplication of scalars elements from the ring R is also commutative. And if R x is a ring with identity, then one can easily see that that identity element must be the identity element of the ring R itself, and similarly one can also argue the third property that R x is an integral domain if and only if R is an integral domain. We will not discuss the proof of this is left as an exercise. This is a simple thing to check by yourself. Now, so far we have defined polynomials over a ring on one variable. One can extend this definition to polynomials over multiple variables. For example, if you have x and y two variables, then one can define R x comma y is the set of all polynomials on two variables. Now, what does it mean? It will have a constant term a naught, and or one can write 0 0 or 0, and then all other terms are of the form a I j, ijth coefficient is a I j x power I y power j, where I is greater than equal to 0, j is greater than equal to 0. Okay. So, sums, finite sums of this form. So, this summation has finite number of I j's, for which this a I j is non-zero. So, I am not writing the details here. This is a finite sum, and a I j's are from R. And similarly, you can take any finite number of indeterminates, let us say x 1, x 2, x t. One can define polynomials on t variables in a similar way. So, every term will be of the form a I naught, I 1, I 2, I t, x power I 1, x 1 power I 1, x 2 power I 2, x t power I t. And set of all such expressions is the polynomial ring. Now, one can also view a multivariate polynomial as polynomial over a smaller number of variables, a ring over a smaller number of variables. Now, for example, a polynomial x y square plus 2 x y plus 3 x can be plus 4. One can write this as a polynomial over the ring R equal to, let us say R prime equal to R x. First take polynomials over x, and then with coefficients from such polynomials, one can take another indeterminate and take polynomials over the variable y. So, one can think of this polynomial, for example, as a polynomial over y, just one variable y, and so y square. So, let us just to make it little non-trivial, let us add y here and 5 here. So, y square has the coefficient x, then y has coefficient 2 x plus 1, and then y power 0, that is the constant term is 3 x plus 5. So, one can see this as a polynomial over y, where these are the coefficients. These are the coefficients, and where are the coefficients from? Coefficients are from R x. This is from R x. These are polynomials on x. So, one can construct multivariate polynomial ring iteratively, first taking one variable, then polynomials over that polynomial ring with an extra variable, and so on. And then by extension of this result, one can see that if you start with an integral domain R, you take polynomial ring on one variable, it is still an integral domain. You take another variable, it is still an integral domain, because then R x is the integral domain, and then you take R x of y. This is also an integral domain. So, this with any number of variables, the polynomial ring, multivariate polynomial ring is an integral domain. And commutativity, identity, all these properties also hold for multivariate polynomials in the same way. Now, however, there is one thing that is special about R x that is not true for multivariate polynomials, and that is a very important important feature. Which is that, so let us take a field f, f is a field, then f x is a PID, principal ideal domain. Not only this, so what does PID mean? It means that every ideal I of f x is generated by a single element, it is a principal ideal. Not only that, every such ideal has a unique monic generator polynomial. So, there are possibly multiple generator polynomials for the ideal, but there is exactly one among them which is monic. So, every ideal I of this has a unique monic generator. So, the proof of this is along the same lines as we have discussed before, for example, the fact that integers z integer ring is a PID and so on. So, we can choose the generator for any ideal. So, given an ideal, given ideal, we choose, let f x be the monic. So, every given ideal and it is non-zero, then there is a non-zero element, and there is a, take the monic polynomial of smallest degree. Let that be f x. Then the claim is that every other element in the ideal is a multiple of f x. So, take any other polynomial, take any g x in I, then one can divide g x by f x and write g x equal to quotient times f x plus r x, where degree r x, degree of r x is less than degree of f x. Right. Now, we will now show that r x must be 0. Why? Because r x is equal to g x minus q x f x, and because g x is in I, f x is in I, this is also in I, and if r x is non-zero, then it is a smaller degree polynomial than f x, and because f is a field, it is a polynomial over field, you can divide by the leading coefficient and get a monic polynomial which is also in I, and it is of smaller degree than the degree of f, which will be a contradiction. Right, because there is supposed to be no polynomial of smaller degree than f in the ideal. Now, by the by the choice of f x, it is clear. So, f x is a generator and this is a monic polynomial of smallest degree. Now, if there are two such polynomials, clearly each of them divides the other, right. So, if there are two polynomials which satisfy this condition, two monic polynomials f and f prime x, f divides f prime x and f prime x divides f x, then clearly they are and they are both monic, then clearly their quotient must be 1, which means f x equal to f prime x. Now, in contrast to this, if you take multivariate polynomial ring f x y, this is not a PID. Why? You can take a specific ideal and show that there is no generator for that ideal. In particular, take the ideal generated by x and y. Take this set and take the ideal generated by this set, okay, which is basically of the form set of elements f x times x, x f x plus y x f x y plus y times g x y, where f and g are from f x y. This is the ideal generated by x and y. Now, one can easily argue that there is no single generator polynomial for this ideal. Okay. We will now define GCD of two polynomials in the same way that we define GCD of two integers. For actually one can define in the same way GCD of multiple polynomials, any number of polynomials. Let us say you have polynomials f1, f2 up to ft over fx. F is a field and fx is the polynomial ring over f. We take t polynomials f1, f2 up to ft. The GCD of these polynomials denoted by GCD of f1, f2, ft. This is the unique monic polynomial of highest degree that divides all the polynomials f1, f2 up to ft, degree that divides f1, f2 up to ft. That means, it is the monic highest degree common factor of all the polynomials. So, it is a common factor of all the given polynomials and it is among the common factors, it is of highest degree. In case of integers, we simply say the largest or highest common factor. Now, for polynomials, there is no such concept of larger polynomial or smaller polynomial, but there is a degree which can be ordered that way, and so we talk about the largest or highest degree polynomial, that is a common factor. There may be multiple polynomials of the same degree which are factors of these polynomials. So, that is why to make it unique, we take the monic one, that is with the leading coefficient 1. So, that makes this unique. LCM is also defined in the same way, least common multiple of polynomials f1, f2 up to ft. This is the smallest degree monic polynomial that is divisible by all these polynomials. That is, it is the smallest degree monic common multiple of these polynomials. The smallest degree monic common multiple. of f1, f2, ft. Now, equivalently one can also define GCD as the monic common factor of f1, f2 up to ft, which is also divisible by any other common factor. So, it is a common factor which is special, which is such that it is divisible by all common factors. So, that makes it also the largest degree, right, because a larger degree polynomial cannot divide a smaller degree polynomial. So, but we will see why these two are equivalent in the next result. In fact, the next result will give us a lot of insight about the nature of GCD of polynomials. Okay. Let f1, f2, f2, ft be polynomials over f, and not all of them are 0. There is at least one of them which is non-zero. Then there exists a d in f(x), that is, these are polynomials. We are not writing f1 of x and so on to reduce notation. D, there exists a d which is unique, a unique d which satisfies the following properties, such that 1, d divides fi for all I, that is, it is a common factor of the given polynomials. 2, that it is divisible by every common factor of these polynomials. So, if C is a polynomial which is a common factor, C divides fi for all I, then C divides D. Every common factor divides that given factor D. And 3, D can be expressed in the form D equal to B1 F1 plus B2 F2 BT FT, where B1, B2 to BT are from Fx. So, this is similar to Biot's lemma in the case of integers. If you remember, the GCD can be expressed in this form, and the same result basically holds for polynomials as well. So, this result, that there is a unique such D which satisfies these properties, it makes this D polynomial the GCD. You can see that these two requirements, that D is a common factor of the FIs and every common factor divides D. Because of these two properties, D must be the GCD of the polynomials, right. So, D is the GCD, you can note that. Now, it says, the third property says that GCD can be expressed in this form. So, let us prove this. We consider the set of all expressions of this form. Okay. So, take the set of B1 F1 plus up to BT FT, B1 up to BT from F. Then these are this forms an ideal clearly. This is from Fx. This is an ideal, and because Fx is a principal ideal domain, this ideal has a unique monic generator, which is the unique monic smallest degree polynomial in this ideal, right, that generates this ideal. So, let D be the unique monic generator of J. The claim is D satisfies all these properties 1, 2, 3. Now, we have already seen that this D will generate this ideal. So, D divides all the polynomials in the ideal, in particular f1, f2 up to ft, because those are also elements in this ideal. By taking b1 equal to 1 and all the other b2, b3 up to bt to be 0, we get f1, and similarly every other polynomial f1, f2, f3 etc., can be obtained, and they are in this ideal. So, D divides fi's, that is obvious. Then D divides fi for all I. Now, if we have a common factor C which divides all the polynomials fi's, now we will prove the third property is, now this holds by choice. This is 1 and 3 holds obviously, because D is an element in J, and so every element in J has this expression is of this form. So, D is of this form. So, 3 is proved, and because D is of this form, every common factor which divides fi divides every coefficient here, b1, every component, every term b1 f1, b2 f2, each of them is divisible by D, divisible by C, any common factor of fi's. So, as a result, C divides D also. Okay. C divides D, since D is of this form, b1 f1 plus bt ft. Now, it is often useful to be able to compute this expression for the GCD. We know that the GCD can be expressed in this form for given polynomials, but how do we find out what these b1, b2 up to bt are for given polynomials f1, f2 up to ft? How do we find out these coefficients, so that that particular combination gives us the GCD? Well, we already know how to find GCD of polynomials, and is very similar to integers, finding GCD for integers, that is using Euclid's division algorithm, and we can find GCD of polynomials in the same manner. And in that process, we also can get these b1, b2 up to bt. So, let us see this through an example. We consider the field f equal to f3, which is basically Z3, that is 0, 1, 2 under addition and multiplication modulo 3. Because 3 is a prime number, this is a field. Now, we take polynomials f1x, two polynomials f1x equal to x cube plus 2x plus 1 and f2 equal to 2x square plus x. How do we compute the GCD of these two polynomials? We use Euclid's division algorithm. We take one polynomial of higher degree, we divide it by the other polynomial. So, 2x square plus x, we divide the polynomial x cube plus 2x plus 1. So, the 2 times 2 is 1 in f3, okay, because 2 is a 4 and 4 modulo 3 is 1. So, we take 2x, we multiply 2x with 2x square, we get x cube, because 2 2s are 1 and x times x square is x3. So, you get x3 and 2x times x is 2x square. So, we subtract, this term cancels, this cancels, we get minus 2x square, and minus 2x square, basically minus 2 is same as 1 in f3, Z3, because 1 plus 1 plus 2 is 0 modulo 3, and so 1 is the additive inverse of 2. So, instead of minus 2x square, we will write it as x square. So, x square plus 2x plus 1, and then we again take plus 2, we get x square plus 2x. If you subtract, we get 1, and then with 1 we need to divide 2x square plus x, and we know that it divides 2x square, 1 divides everything. So, 2x square plus x, 2x square plus x, and we get 1 as the GCD. So, the GCD is 1. Now, how do we express this as some polynomial times f1x plus some polynomial times f2x? Well, one can see what happened in the first division. Well, let us go from the end. We can first express what happened in the second division. We see that 1, this GCD 1 is basically 1 is the GCD. So, we can take the first division and write the remainder 1 is equal to x cube plus 2x plus 1 minus quotient times the 2x square plus x. So, we get 2x plus 2 times 2x square plus x. So, that expresses it in the required form. This is our f1x, and this is minus 2x plus 2 times f2x. Right. So, if there are multiple more number of divisions, we could backtrack and finally get an expression in terms of f1 and f2. Okay, we will now discuss factorization of polynomials and about irreducible polynomials. We have discussed a result before about PIDs. We have seen that if we have R is a PID, then and if you have an element A which is prime in R is prime if and only if R by the ideal generated by A is a field. Okay. So, now we will apply this to the polynomial rings over fields, and this will give us a version of this result in particular. So, polynomials are of special interest to us. So, let us write down that result. F is a field and f in fx is a polynomial which is irreducible. This is if and only if fx by the ideal generated by f is a field. This directly follows from this result which we discussed before, because fx is a PID, we have seen it. So, f is irreducible means that it is a prime element in the ring fx, because the definition of irreducible means that it has no non-trivial factor. So, now this is a very simple consequence of this more general result, but it is highly important result, because it allows us to construct bigger and bigger fields. If you start with a small field f like f2 or f3 filled with 2 elements or 3 elements, which can be constructed for any prime number p, one can construct a field with p number of elements by just taking modulo p addition multiplication in the integers 0 to p minus 1. We can then take an irreducible polynomial f and take this quotient. Okay, we will get a field which will have polynomials as elements and it will be an extension field, a bigger field than the ZP or FP we had. In fact, this is the standard way of constructing finite fields. Okay. Now, another result we will now discuss is the following. If P is an irreducible polynomial in f(x), and f1, f2, fm are in f(x), these are polynomials, and if P divides f1, f2, fm, the product, then P must divide one of them. P divides fi for some I. This is the result. We know this result for integers. Now, this result also holds for polynomials, and this is what we will show now. Now, because P divides f1, f2, fm, this product, consider the ideal generated by P, ideal of fx. What this means is that the product f1, f2, fm is in the ideal P, right, because it is a multiple of P. What it means is that the corresponding coset is the 0 coset, that is this f1, f2, the coset of this is this, we denote this by this, which is that if you take any element A, which is, let us call this, let us say f, any polynomial f, we denote by this the coset f plus p, coset of the ideal where f is there. Right. So, the coset of f1, f2, this product is the ideal itself, that is the 0 element, the coset of 0. Now, set of cosets form the coset, the quotient ring, which in this case is a field, because P is irreducible. We just now discussed, if P f is an irreducible polynomial, then this quotient ring is a field. So, if P is an irreducible polynomial, this is a field f by, so this is in fx by P, right, and this is a field. Now, the left hand side is same as f1, f2, the product of the cosets of f1, f2 and fm. This is same as 0. Now, these are elements in this field. So, the product of these elements is 0 in the field, and a field is of course an integral domain, which means that at least one of them must be 0. That means fi is 0 for some I, that is fi is in P for some I, which means that P divides fi for some I. Okay. Now, we come to the a very famous result for polynomials, which is the unique factorization theorem. This says that any polynomial in fx, let's take f, has can be expressed f equal to a p1 any polynomial f in f x can be expressed as this, where these pi's, that is p1, p2 up to pt, are irreducible polynomials monic irreducible polynomials. Furthermore, this expression is unique up to ordering. This expression is unique up to order. That is, you can get a different expression by reordering these terms, the factors, but fundamentally no other expression can be obtained other than by reordering. So, we will not discuss the proof in detail here, but it is quite simple argument. First of all, the fact that any polynomial can be expressed in this form can be argued simply by factoring again and again till you get every factor as irreducible. If f has irreducible has non-trivial factors, we can factorize them into smaller degree polynomials, and then those factors again can be factored again and again until we get all the factors as irreducible factors. So, then we combine all the same factors together and write it as a factor power an exponent, and then we get an expression of this form. While leading to make all of them irreducible, we can take out the leading coefficients as outside and then write that as a. So, now the interesting part is also the uniqueness. So, if you have two different expressions of the same form, that is a p1 e1 pt et is same as b, let us say q1 q1 alpha 1 up to q s alpha s for the same polynomial, these two are same, then one can easily see that p1, suppose p1 has a positive exponent on the left hand side, then p1 divides this left hand side. So, p1 must divide the right hand side also. Now, if p1 divides the right hand side, then because p1 is an irreducible polynomial, it must divide one of the factors, and so one of these irreducible polynomials must be p1. So, you can then remove p1 from both sides, you can divide by p1, the equality would still hold, and then we can keep on arguing that p1 by repeatedly applying this argument, one can show that the exponents also will be the same, and so on. So, any polynomial has a unique factorization into as a product of irreducible polynomials. This is the summary. Okay, that is all for now.